All right. Yesterday, we were talking about calculating the Avogadro's constant by an electrolytic method, and the method was simple. The Avogadro's constant was given the symbol capital L, and that was equal to charge on 1 mole of electrons divided by charge on 1 electron. And by dividing it, we'll simply get the value for 1 mole, or which is Avogadro's constant, which was 6.02 into 10 raised to power 23. Okay, if you remember that from AS or from O levels. Now, in this whole thing, what's important is that we calculate the charge on 1 mole of electrons, because we already know the charge on 1 electron is 1.60 into 10 raised to power minus 19 coulombs. So in order to find charge on 1 mole of electrons, what we are supposed to do over here is to go with an experiment given in this pink portion. Getting started with the experiment, the charge on 1 mole of electrons can be found by a simple electrolytic experiment. Take a look at this experiment that both the electrodes, the cathode and the anode, are made out of copper. The electrolyte is also a copper salt solution, which is aqueous copper 2 sulfate. We are using a power supply system. We are using a direct current power supply system, as we explained yesterday. Okay. And there is an ammeter which shows the current that is present in the circuit, and there is also a variable resistor present in the circuit. I hope you're familiar with both from physics, that a variable resistor and an ammeter can help us in the circuits. Ammeter to show how much the current there is, and variable resistor in which we can change the resistance according to our need. Now, why are we going to change the resistance? We are going to quote that over here. This is the apparatus for calculating the mass of copper deposited during the electrolysis of aqueous copper to sulfate. The procedure is we weigh the pure copper anode and pure copper cathode separately before the start of the experiment. Then we arrange the apparatus as given in the experiment's diagram, and the variable resistor is used to keep the current constant. Okay. Here he states why are we going to use the variable resistor. Now, moving on, how do we do that? You'll come to know that in later steps. Pass a constant electric current for a measured time interval. Now, remove the cathode and anode and wash and dry them with distilled water, and then with propanone. Okay? First of all with water, then with something that is organic, see, and reweigh the cathode and anode. Now, the cathode increases in mass because copper is deposited. The anode decreases in mass because the copper goes into the solution as copper ions. The decrease of the mass of anode is measured. This is preferred because copper does not always stick to the cathode very well. Okay? So that's how we know. What we are going to do is that first of all, this should be equal. Copper depositing over here, copper depositing over here on the cathode, and the copper leaving the anode should be equal. But what happens over here is that sometimes copper is not able to stick properly on the cathode. So there are more amount of copper atoms converted into ions and lost into the electrolyte than the ions moving from the electrolyte and getting deposited on the cathode as atoms. I hope you're familiar with this entire process as from IGCSE, the same chapter, but it wasn't a part of electrolysis, it was a part of electroplating. This experiment was used for copper plating, if you remember that back from IGCSE. Now moving on, a simple calculation is shown below using a current for 0.2 ampere for 34 minutes. Mass of anode at the start of the experiment was 56.53 grams G.
सॉरी सर, वो सर आपने अभी बताया जो कि उनके दोनों के इक्वल होने चाहिए लीविंग और जो डिपॉजिट है, तो सर वो इक्वल नहीं होते क्या?
Theoretically speaking इक्वल होने चाहिए, but they are not equal. The reason is given over here because copper does not always stick to the cathode very well. Sticking capability of ions depend upon the size of ion, the charge of ion, stuff like that. The battery voltage or the current strength of current in the battery, different things. So that is something of higher level beyond the requirements of A level. So let's just stick to the point that copper does not always stick to the cathode very well.
Yes, sir.
All right. So for the calculation, 0.2 amperes for 34 minutes. So the mass at the start of mass at anode, start of experiment 56.53, and at the end of experiment 56.40. Some of the mass is lost in terms of the atoms were converted into ions and were lost as a part of electrolyte. Mass of copper removed from anode is very simple, 0.13 gram. It's a subtraction step. Quantity of charge passed, 0.20 multiplied by 34, as 34 is minutes, multiplied by 60 to convert it into standard unit seconds. And we have 408 coulombs for that purpose. So to deposit 0.13 grams of copper requires 408 coulombs. To deposit 1 mole of copper, 63.5 grams, would require 63.5 divided by 0.13 multiplied by 408 coulombs. Okay? But the equation for the electrolysis shows that there are 2 moles of electrons that are needed to produce 1 mole of copper. So whatever's we are getting over here, we're going to divide that by 2. So instead of dividing this answer by 2, he multiplied the whole thing by the fraction half. So 1 by 2. So what we get over here is 99,600 coulombs. If the charge on one electron is this, the charge on 1 mole of electrons is this, we divide that for the equation of L, that was Avogadro's constant, and it's approximately 6.2 to 10 raised to power 23, which is in good agreement to the accurate value 6.02 into 10 raised to power 23. Remember, this is 6.2 and this is 6.02. But still, we call that a good agreement with the accurate value. Any questions from this part so far?
Nice.
All right, moving on. Sorry. There are a couple of questions related to this process. These questions are very much similar to what we can get as a part of paper 5, right? So if you do this calculation and if you do these two numericals according to this calculation, this is mostly important for paper 5. However, this has also been a part of paper 4. Electrode potentials, next topic. Introducing electrode potentials. A redox equilibrium exists between two chemically related species that have different oxidation states. For example, when copper rod is placed in contact with aqueous solution of its own ions, this equilibrium exists. What we are trying to say over here is that the reaction starts, but we are not able to see any change because the reaction goes to a proper equilibrium. And if you remember equilibrium from IGCSE, you would remember that that was a central state of the reaction in which the rate of forward reaction was equal to rate of reverse reaction. So we couldn't find a big change in the reaction. Why? Because the both rates were equal to one another and actually cancelling each other's effects. So copper ions become in equilibrium with the copper atoms or copper solid whenever we place a copper rod in contact with aqueous solution of its own ions. So there are two opposing reactions in the equilibrium. Now we are going to go with the forward reaction for this one and the reverse reaction for this one. The forward reaction is the one in which the ions, this is the forward reaction, the ions in the solution are getting electrons and are being converted into atoms. But the reverse reaction would be metal atoms are actually converted into ions by giving out electrons. Now, the reaction on top over here is oxidation, loss of electrons. And the reaction over here is reduction, gain of electrons. When these two reactions are written in a combination as a reversible reaction, it looks like this, which is actually an equilibrium reaction. But we're using the phrase redox equilibrium in order to show that one of the reactions, either the forward or the reverse, is oxidation, and the vice versa is reduction. So that's why we call it a redox equilibrium. Are we all clear about redox equilibrium?
Yes, sir.
Yes.
Redox equilibrium is established when the rate of electron gain equals the rate of electron loss. For unreactive metals such as copper, if this equilibrium is compared with the equilibrium set up by other metals, the equilibrium set up by copper lies further over to the right. Do we understand that? This is for an unreactive metal such as copper. What he tries to say over here is that for unreactive metals, they tend to stay in this solid form instead of ionic form. And for reactive metals, it would actually be the opposite. They will try to react quickly in order to be converted into ions. Why is that happening in like this way? Let me tell you, the reactive metals are more stable in their ionic form. However, the unreactive metals are more stable in their solid form. That's why the reactions occurs like this for reactive and for non-reactive elements respectively. Do we get the point?
So why are reactive atoms more stable in ionic form?
That we started back in IGCSE as well as in A levels, the bonding chapter. Remember, when the reactive metals are converted into their respective ions, I don't care whether that becomes a cation or an anion, it can be anything. They are actually having a valence shell configuration of the nearest noble gas, which is a sign of stability in their ionic form. However, for unreactive or inert metals, they're actually stable in their own behavior. Why? Because in most of the cases, they're already stable the way they are. Hence, unreactive. That's why the most unreactive elements on the periodic table are what? Are noble gases. Why are noble gases most unreactive? Because
सर वो अपनी वो भी तो कंप्लीट कर सकते हैं वैलेंस शेल बॉन्ड बनाकर भी तो कंप्लीट कर
तो बेटा आयन क्यों बनना बॉन्ड बनाने के लिए तो है, इसके बाद बॉन्डिंग भी हो जाएगी. Once they are in the form of ions, they have electrostatic forces of attraction that can easily form ionic bonds. Right? Do you get the point? What you're saying is true, but what I'm saying is the preliminary step of what you're saying is a prerequisite. You can't form an ionic bond before making an ion, right?
Yes.
Good, good. So, Asher, you're saying 21. What's 21?
वो सर गलती से टाइप हो गया था, मैं कुछ और ढूंढ रही थी, वो टाइप हो गया, चैट खुल गई थी इसलिए सॉरी.
Okay, okay. I thought it was a question.
No sir.
Okay.
Sorry.
Okay. It's okay. No problem. So, do we get these last two lines? So, copper tend to stay in the form of solid copper. Copper ions are therefore relatively easy to reduce and they can gain electrons readily to form copper metal. So they tend to go towards their stable forms, and that's easier. When they are in their unstable forms, they will always tend to go to their stable form and the process would be easier. However, the vice versa, the opposite process would be somewhat difficult. For example, in case of reactive metals, they tend to stay in the form of ions. So the conversion of atom to ions would be easier, and the conversion of ions back to atoms would be difficult. That's why all the sodium that we find on this planet is never in metallic form. It's always in salt form, right? But most of the copper that we find on this planet is present in its native form. Not just copper, silver, gold, platinum. They're present in their native forms. Why? Because they are stable that way. Hence, on the other hand, sodium, potassium, calcium, magnesium, these are usually present in the form of compounds, never the native metal. Why? Because it's not stable that way. I hope the whole thing is cleared by these examples. And if it's clear, we can move forward. For a reactive metal. Right. O levels chapter number 8, Reactivity of Metals. For reactive metals such as vanadium, the equilibrium lies further over to the left. I've already explained that with examples. For example, I talked about sodium, potassium, calcium, magnesium. But as they're discussing more about transition elements, So they took a reactive metal from the transition elements, example of vanadium, and they also talked about an inert element from transition elements, hence copper. So they gain electrons much readily by comparison. The position of equilibrium differs for different combination of metals present in the solutions of their ions. So when a metal is put into the solution of its ion, an electric potential voltage is established between the metal and the metal ions. We cannot measure this potential directly, but we can measure the difference in potential between a metal or a metal ion system and another system. We call this value electrode potential, capital E. Electrode potential is measured in volts as there is a potential difference. So hence voltage difference, hence volts, the standard units. The system we use for comparison is standard hydrogen electrode. This is a standard electrode system that we use for comparison. For example, अगर हम कॉपर को कॉपर में प्लेस करेंगे, कॉपर मेटल को कॉपर आयंस के सॉल्यूशन में प्लेस करेंगे, हम इसका वोल्टेज सेपरेटली फाइंड आउट नहीं कर सकते. हम वेनेडियम आयंस को वेनेडियम मेटल को वेनेडियम आयंस के सॉल्यूशन में पुट अप करेंगे, हम इसका वोल्टेज डायरेक्टली फाइंड आउट नहीं कर सकते. इसको इलेक्ट्रोड पोटेंशियल बनाते हैं, लेकिन इसको फाइंड आउट करने के लिए हमें इसके साथ इसे कनेक्ट करना पड़ता है इन कंजंक्शन टू अ स्टैंडर्ड और अ रेफरेंस सिस्टम. That standard or a reference system is actually standard hydrogen electrode, which is our next topic in detail. All right. It is thought that absolute electrical potentials that we cannot measure are caused by the formation of electrical double layer when an element is placed into a solution of its own ions. अब वो इसकी reason भी बता रहा है, हम directly क्यों नहीं measure कर सकते, ठीक है. फॉर एग्जाम्पल अगर हम एक कॉपर का छोटा सा पीस लेते हैं और उसे कॉपर के सोल्यूशन में डिप कर देते हैं, उसके अंदर वोल्टेज चेंज भी आ रहा है, लेकिन वो डायरेक्टली फाइंड आउट नहीं हो सकता जब तक हम उसके साथ एक रेफरेंस सिस्टम यानी स्टैंडर्ड हाइड्रोजन का इलेक्ट्रोड नहीं लगाएंगे, ठीक है. तो वो क्यों नहीं फाइंड हो सकता, क्यों? क्योंकि उसके ऊपर फॉर्मेशन होती है इलेक्ट्रिकल डबल लेयर की. फॉर एग्जाम्पल, a piece of zinc is placed in a solution containing zinc ions. A tiny number of zinc atoms on the surface of the metal are converted into zinc ions, which go into the solution. This leaves an excess of electrons on the surface of zinc. The solution around the metal has now excess of zinc positive 2 ions. Some of these cations near the surface of zinc are attached to its surface. So an electrical double layer is formed. This is built up of a charge, causes an electric potential between the metal in the solid form, of course, and the metal ions in the solution. Take a look. We took a piece of zinc which is placed at the center. As soon as it started losing some ions as zinc plus 2 ions, which are given in circles on the right and the left hand side of the zinc rod. But as they left out of the system, they left a few electrons as a part of oxidation process, which remained on this zinc rod. So the zinc rod consists of extra electrons on its outside, which tends to attract the nearby zinc ions, forming a double layer. Take a look. It's a double layer. A negative layer, a positive layer. And on the other side, we also have a double layer, a negative layer, and a positive layer. This buildup of double layer of ions is actually the reason why we cannot measure the voltage directly, because all the voltage is concentrated at one point, the double layer. Also, we call the double layer hindrance towards the calculation of the stand voltage all by itself. What we do is that we are going to attach in conjunction to this system a standard system or a reference system in which we will be able to calculate the difference between both. Now let's talk about the standard system first. Then we're going to connect this to the standard system and find out how we measure the electric potential. Talking about the standard system, that is known as the standard hydrogen electrode, commonly abbreviated as SHE, S-H-E, standard hydrogen electrode. So SHE is one of the several types of half cells that can be used as a reference, that can be used as reference electrodes. Take a look at this figure. Now, as we're talking about a hydrogen electrode, so what we need over here is the container. The container should contain a system in which we have hydrogen ions. So we usually commonly use an acid for that purpose, because acids give away hydrogen ions. The molarity or the molar concentration should be a standard, hence 1 mole per decimeter cube solution. Then what we are going to do is that we are going to cover the entire thing with a glass tube. Why are we doing that? Because if you're talking about hydrogen in its natural form, it cannot be present in the form of a bar or an electrode. Copper can do that, vanadium can do that, zinc can do that. Hydrogen, on the other hand, is a gas naturally, a diatomic molecule. Okay? So what we do is that we go for a glass covering, and inside that glass covering, we supply the hydrogen gas at a pressure of 1 atmospheric. Once again, the standard. Remember, 1 atmospheric was a very large unit, and when we converted into system international units, Newton per meter square, the value was equal to 1.01 multiplied by 10 raised to power 5, for which we used to call it 0.1325 for the exact figure or the exact value. Now, what we do is that we take this platinum wire all the way passing through this glass tube. Down at the bottom, we have a platinum electrode, the best electrode on the planet, the most inert one and the best one according to its progress. And then there is a glass bell with a hole in for hydrogen to bubble out of the system. There you can see a small hole on the side, and as hydrogen is a colorless gas is bubbling out of the system. So this is hydrogen electrode. This is the reference electrode that we're going to attach with this one, the zinc one, and we're going to calculate the electrode potential of the zinc ion. How do we do that? There are a few things that we need to still study about this electrode before we can connect it to that one. This electrode consists of hydrogen gas at 101 kilopascal pressure. Newton meter and Pascal is the same thing. So that's GL1.
सर इसका क्या कहते हैं, हम इलेक्ट्रोड पोटेंशियल जो है उसी के लिए क्वालिटेटिव एनालिसिस के लिए कैलकुलेट करेंगे?
नहीं, क्वांटिटेटिव, हम एक्चुअल मैथमेटिकल वैल्यूज फाइंड आउट करेंगे. क्वांटिटेटिव एनालिसिस होगा, क्वालिटेटिवली भी क्वांटिटेटिवली भी, दोनों कहना चाहिए.
उसका क्या कहते हैं सर, फार्मूला वगैरह कोई अभी हमें पता होना चाहिए उसके अलावा, फिर आने वाले के अलावा?
इतना छोटा सा फार्मूला होगा कि वो बहुत इजी होगा, लेकिन पहले इसे समझना जरूरी है. पहले इसकी अपनी वैल्यू पता होना जरूरी है, इससे पहले कि आप किसी रेफरेंस सिस्टम को उसके साथ लगा सकें. फॉर एग्जांपल, जब आप लेंथ मेजर करनी होती है तो आपको अपना जो फुट स्केल होता है, जिसकी हेल्प से आप किसी भी चीज की लेंथ मेजर करते हैं, उसकी अपनी स्टैंडर्ड रीडिंग्स पढ़नी आनी होनी चाहिए. आपने अगर टाइम मेजर करना है और आप स्टॉप वॉच यूज कर रहे हैं, तो आपको स्टॉप वॉच यूज करना आना चाहिए कि हमने उसे कैसे रीड करना है. सो बिफोर वी कनेक्ट दिस वन टू दैट वन, हम दोनों इलेक्ट्रोड्स को इन कंजंक्शन इस्तेमाल करें. सबसे पहले हमें इस इलेक्ट्रोड के लिए वैल्यूज पता होनी चाहिए, और वही हम एक्सप्लेन करने जा रहे हैं. फॉर्मूला की जहां तक बात है, बहुत छोटा सा, बहुत इजी सा फॉर्मूला होगा. ठीक है, वो जैसे ही मैं इसकी वैल्यू बताऊंगा, आपके ऑटोमेटिकली ज़हन में आ जाएगा कि उसका फॉर्मूला क्या हो सकता है. ठीक है, क्लियर?
जी सर, थैंक यू.
Welcome. The electrode consists of hydrogen gas at 101 kilopascal pressure in equilibrium with hydrogen ions at a concentration of 1 mole per decimeter cube. Remember, both these values are a standard system value. The platinum electrode covered with platinum black in contact with hydrogen gas and the H positive ions. Now, students tend to ask the question over here, what is platinum black and why a platinum electrode is again covered with platinum black? Now, let me tell you, platinum black is actually the finely divided, or you can say powdered form of platinum. Remember, I told you that the word powdered is used for all other things except a metal, because a metal cannot be powdered. It can only be finely divided. So platinum black is actually finely divided form of platinum, which we actually paste on top of this square black platinum electrode. Why do we do that? To increase its surface area, in order to increase its efficiency. And when it comes in contact with hydrogen gas and the H positive ion, the whole equilibrium is established. See? The platinum black is the finely divided platinum, which allows close contact of hydrogen gas and H positive ions in the solution. I've already explained this. So that equilibrium between hydrogen gas and hydrogen ions is established quickly. Hence, the working or the reason for platinum black. The platinum electrode is inert, so it does not take part in the reaction. Standard electrode potential, which is taken as E0, values for all half cells are measured relative to this electrode. When connected to another half cell, the value read on the voltmeter gives the standard electrode potential of that cell. Very easy. This gives us the equation. Okay? But there is one more thing to learn over here. The half equation for hydrogen electrode can be written in this form or in this form. See, both ways it's fine. The way that half equation is balanced makes no difference to the value of E naught. Hence, both ways are fine. The equation does not affect the tendency for the element to gain electrons. The equation will not change the tendency. So whether we write it like this or we write it like this, the tendency for gaining electrons for an atom or losing electrons for an atom will not change. So before I move on to the next point, let me tell you something which is not written over here. The voltage for this cell is actually arbitrarily, which means hypothetically or on purpose, intentionally taken as 0. It's not exactly 0, it's close to 0, but is taken as 0. Now, if the standard cell or the standard system is 0, whatever is the value of the conjunction system or the system we join it with will remain the same. Now, if the voltage for zinc system is 2, as this is 0, 0 plus 2 would remain still 2. If the value is minus 2 for the system and this is 0, so 0 minus 2 would be minus 2. Okay? So this has as a standard or an arbitrary value of 0. Hence, whenever the system is combined with any other system, the value of any other system remains the same. Right? So, electrode potential and redox reactions. Electrode potential values give us an indication of how easy it is to reduce a substance. For example, let's take a look. By convention, the electrode potential refers to the reduction side, reduction reaction. So by convention, it's not important that everything goes to reduction. No, that is not important. You already know metals tend to go for oxidation. They try to lose electrons and they try to form positive ions. On the other hand, the non-metals, they tend to gain electrons and form negative ions. But we don't go by that way. What we do as a worldwide convention that we write reduction reactions for everything. So for non-metals, it's very simple. They're already reducing, so the reduction reaction would be simple. But for the reduction reaction of metals, we'll have to use the reverse equation, and the reverse equation is given over here. Like you can see, this equation is already reversed. Metal tends to lose electron, but in this equation, the metal is actually, the ions of the metal are gaining electrons to form the solid metal. Okay? So the electrons tend to pair on the left-hand side of the equation for all the equations in the calculation of electrode potential. So, second point, the more positive or less negative the electrode potential is, the easier is it to reduce the ions on the left. Okay? So, the more positive this value gets, the bigger this value gets, or less negative, smaller value negative, will make sure that this compound likes to reduce from ions to metallic form. Are we clear? Are we clear with the second
Yes,
point?
sir.
Good. Which means the metals on the right is relatively unreactive, is a relatively poor reducing agent, because metals tend to be reducing agents, but the reactive ones are good reducing agents. On the other hand, the metals that are unreactive are poor reducing agents. Whether we define it this way or we define it on the basis of reactivity separately, both things say the same thing. So this proved that electrode potentials is another way of verifying the reactivity of metals based upon their electrode reactions. Coming to the third point, the more negative or the less positive, the smaller this value will get, the more difficult it is to reduce the ions to the left, which means the element is relatively reactive and is a good reducing agent. instead of reduction, it tends to oxidize more. So more reactive elements actually give us bigger values in negative. For example, sodium, for example, potassium, for example, calcium. These elements will tend to give us the largest negative values possible. Are we clear?
Yes.
Now,
Yes,
this
sir.
exercise is a very good childish exercise. I tend to do this exercise on my own if they're not present as a part of the book. But here, the exercise is present as a part of the book. Now, taking a look, as we have all the students in the class, let's go by these questions one by one. You have the question number 10, all the equations, all the voltages in front of you. Let's answer them one by one. Who are we going to start with? A for Rohma, B for Aisha, C for Fuzema, बच्चे को छोड़ देते हैं, D for Ali. अलवान बस enjoy करें सारों के आंसर्स, ठीक है? So starting with A.
सर डी से शुरू कर
D से शुरू कर लें, चलिए D से शुरू कर लेते हैं, starting with
सर
Ali.
ई से शुरू कर लें, अलवान से।
E में कोई question नहीं है.
So reducing best Ag होगा silver.
Sorry. What did you just say?
D का which metal ion in the list is the easiest to reduce?
Oh, your
Silver
question is
is the
different.
easy.
Sorry, I didn't realize that. Yeah, D. Which metal ion is in the list is easiest to reduce? So that is
Silver ion. Silver
and
ion.
why are you saying that?
Because it has the most positive voltage, and more positive mean it is a better oxidizing agent.
Or easier to reduce, right?
हाँ, easy to reduce. जी sir.
Good. Oxidizing agent आप तो कह लेंगे, आपने अपने एंड पे समझ लिया, ये ना क्लास में तो और बच्चे कंफ्यूज हो जाएं, ठीक है? So let's stick to the wording of the book or the question, ठीक? Okay, good answer by the way. So C part, Hosaima, your turn.
Sir, zinc is the most reactive because it has the most negative voltage, that is minus 0.76.
Very good. B part, Aisha.
So zinc, because it's more negative, then the more difficult to reduce.
Very good. And A, Roma.
सर CO because it's the most negative.
What? C isn't the most negative.
Sorry sir, zinc. Sorry sir.
It's the
Zinc
best
is the most
reducing agent.
negative.
Yeah,
जी,
most negative and hence is the best reducing agent. Good. So I hope we understand all of these questions. Do you have any questions before we move any forward?
No, sir.
No sir.
What about E? E, do you have a question or are we good?
Yes, sir.
Okay, good. Combining half cells. Finally, the point where we need to combine them both in order to find out the values for these cells. Okay. In order to measure the electrode potential relating to half equation, let's take copper as an example. Take a piece of pure copper, dip it into a solution of copper sulfate, the blue solution, of course, the piece of copper. This would become a copper ion / copper system. This is a proper way of writing this. So mind that we're going to use this way of writing a lot in the coming portions. See? So we use the standard conditions to make the half cell. Number one, copper ions are present in the condition of 1 mole per decimeter cube. I've already told you that. The temperature is 25 degrees centigrade, which in standard units is 298 Kelvin. Understandable. The copper rod must be pure. These are the prerequisites. Okay. This is a common short question in past papers, and this is very easy to explain over there. However, what he does is that he tends to change this question with some other metal rather than copper. Once again, all the things would remain the same, just the name of or the symbol of the element would change. So that's very easy to answer. If we connect two half cells together, we have made an electrochemical cell. Electrochemical cells, as I explained previously, can convert chemical energy into electrical energy or vice versa. It can either do one or it can do both. That depends upon the cell. We can measure the voltage between these two half cells. This figure shows a copper ion copper half cell. This is known as copper ion copper half cell. The ones with the pluses or minuses are the ions, and the one is written in simple is the element. So no matter what's the order between them, it would be said in the same way: copper ions copper, or copper copper ions half cell, whatever that is. They get connected to zinc ions zinc half cell to make a complete electrochemical cell. Half cells are connected together using wires connecting the metal rods in each half cell to a high resistance voltmeter. The electrons flow around this external circuit from the metal to the more negative or less positive electrode potential to the metal with a less negative or more positive electrode potential. Of course, it is going to move from the one that is losing the electrons to the one that is gaining the electrons, or what we can call from oxidation part of the process to reduction part of the process. Of course, it's going to work like that. See, and we use the salt bridge, something new that we need to explain over here, to complete the electrical circuit, allowing the movement of ions between the two half cells so that ionic balance is maintained. A salt bridge does not allow the movement of electrons, it only allows the movement of ions. A salt bridge can be made from a strip of filter paper or other inert porous materials soaked in a saturated solution of potassium nitrate. See, let me show you the diagram. This is how we're going to place it. The copper system with copper ions, 1 mole per decimeter cube in solution, the electrolyte, and a copper rod in here. The zinc system, the zinc part, a half cell part, zinc ions, 1 mole per decimeter cube, and the zinc rod dipped into it. The outside portion is connected with metallic wires, high resistance voltmeter, and the inside of the system is connected with salt bridge. This completes the circuit. So take a look. From these ions, this rod, through this wire, through the voltmeter, through this wire, all the way to this rod, to the ions, and then through the salt bridge, the current will travel. And that's how the whole circuit is completed. If we don't put a salt bridge, it would start working and stop after some time when all the electrons from one side have moved all the way to all the electrons on the other. So yes, it would start working, but it would still stop eventually. In order to keep the process running, the salt bridge is important. जी बेटा.
सर ये salt bridge salt का बना हुआ होता है?
Yeah, as
This
stated
is
above, potassium nitrate. If not potassium nitrate, potassium chloride has also been used as a part of salt bridges. They are usually
सिर्फ क्या
present
मतलब कोई
in
प्लास्टिक है जिसके ऊपर सिर्फ वो किया हुआ होगा, पाउडर किया हुआ होगा?
good idea, but not plastic, and immovable gel, which has small pores, and inside the pores we have the chemical.
Sir,
Potassium nitrate,
immovable and unreactive too.
not exactly unreactive. It
Okay,
reacts,
sir,
but it does not react completely. The concept of salt bridge is a little bit complicated, but the point here is that it allows a few certain types of ions to pass from one side to another in order to maintain the ionic balance, in order to keep the cycle running. However, this is the easier form how we tell it to students. This is not entirely or exactly true. The system is, the understanding of salt bridge is a little bit complicated. So what we do, or we tend to say at this point, so let's take an example.